Hello, and welcome to the first video from Unapologetic Maths. Today, I will give an introduction to some of the basics of set theory, a system which underpins all of modern mathematics. Firstly, we ask, what is a set? Simply put, a set is a collection of things. We can have a set of numbers, a set of elephants, a set of letters, even a set of sets. To start with, we will cover a bit of notation. Throughout, I will use illustrations you may be familiar with from Venn diagrams, which are in fact just a tool for representing sets. Each thing inside a set is called an element of the set, and we write that like this. A subset of a set A is a set whose elements are all also elements of A, and we denote that with this symbol. We can also perform certain operations on sets. For example, the union of two sets is the set of all elements in either set. The intersection of two sets is a set of elements that are in both sets. The set difference of two sets is the elements of one set that are not in the other set. When we take the set difference of a set and its subset, we often call this the complement of the subset. We also have special notation for some of the most commonly used sets, such as the empty set. This is a set with no elements at all. The natural numbers. This is a set of all positive whole numbers like 1, 2, 3, and so on. The integers. This is the same as the natural numbers, but with the negative numbers and 0 added in. The rational numbers. This is the set of all fractions. The real numbers. This is the set of all numbers including fractions and so on, but also numbers that cannot be written as fractions, such as pi and e. Notice that each of the sets I have listed contains the previous set as a subset, and that the empty set may be said to be a subset of every single other set. Now, many of you may remember functions from maths at school, but here's a quick recap. Examples of functions include x plus 1, x squared, sine x, the natural logarithm of x, and so on. Using sets, we can now think of functions more formally, as a device that takes in elements of one set and gives you back elements of another set, according to some defined rule. We write the definition of a function like this, to make it precisely clear what we mean. Breaking this down, it says that we have a function called f that sends elements of A, called the domain, to an element of B, called the codomain, according to some rule. To properly define a function, we need it to be defined for each element in the domain and only give one value for each. If this is the case, we say it is well defined. For example, neither of these functions are well defined. To compare, in these reversed cases, the functions shown are well defined, although they do lack certain properties that are useful, as we will see. We say a function is injective if it never maps two different elements of the domain to the same elements of the codomain. So for example, the function on the left is not injective, but the function on the right is. We say a function is surjective if every element in the codomain is mapped to by the function. So for example again, the function on the left is not surjective, but the function on the right is. If a function is both injective and surjective, then we say it is bijective. Now, bijective functions are really important. If we have a bijective function between two sets, then they must have the same size. This is a handy way of telling us that two sets have the same size, even if we don't know what that is, or if they're infinitely big. We call a set countable if we can create a bijective function between it and a subset of the natural numbers. This subset could well be the entirety of the natural numbers. For example, if we consider the integers, we can create a function that sends 0 to 1, 1 to 2, and -1 to 3, and so on, alternating between the positive and negative numbers. We can see that this is defined for every integer, that it never maps two integers to the same natural number, and so it is injective, and that every natural number is covered by this function, so it must be surjective too. So our function is bijective, and thus we have shown that the integers are countable. Now this may seem a bit strange, as the natural numbers are contained in the integers, but since we are dealing with infinitely big sets, this can defy our expectations. Thank you for watching.